Right, good morning. Welcome to the lecture of material science. So, last week, we learned two-dimensional defects, and this is a summary. And then let's uh, record this information together. So, for the two-dimensional defects, uh, the first one is in external surface. External surface is the surface which is um, the made the another phase like liquid or like gas, and also the bonding is not so completed compared to the atoms inside the solid material. So this is what we call external. And then after that, this is in interfacial defects. Defect means that you have many defects inside the material, including ground boundaries. And ground boundaries, this is ground boundary, right? This is ground boundary. And you can divide ground boundaries into some small, some parts. Excuse me. And the first one is small or large angle grams. Depends on the growth direction. The two grams might meet each other in small angle or in big angle. So we have small angle and large angle grams. And we have tilt boundaries and twist boundaries. Tilt boundary actually is the arrays of the dislocation, right? Remember that? For the twist boundary is the arrays of the screw dislocation. Screw dislocation, which is one-dimensional defects. Okay, so and also for the defects we have twins boundaries. Okay, twins boundary means what? Means a line which is you have a mirror, like mirror defects, which if you fold these two faces, two gram together, it will perfectly match to each other. So this is called twins boundaries. And also you have phase boundaries. Phase boundary means you have FCC and BCC, or you have different phases. Phase boundary means that you have different phases, like A phase or B phase. As we know that different type of the material, you have A phase or B phase or alpha beta phase. And after that is called stacking faults. Stacking faults is FCC is ABC stack packing, right? And for a hexagonal closed pack, HCP is that AB or AB AC AB AC ABC AB AB. So this is kind of stacking faults. Okay, so and the next one is what we call ferromagnetic. This is ferromagnetic domain walls. If we don't apply magnetic field to this metal, the metal will randomly distributed. However, if we give a magnetic field to this metal, and the magnetic domain will be aligned to a certain direction. So this is called ferromagnetic domain walls. So this is also one type of defects. So in the energy of two-dimensional defects, external surface will have the highest energy, and then ferromagnetic domain will have lowest energy, because external surface has the highest energy. Means what? That means external surface will have a higher reactivity. It's very, very easy to react with another chemicals. Okay, so this is high energy and will have high reactivity. Okay, for the grand boundary, if we think of the grand boundaries, we have three topics to talk. The first one is high and small angle boundary energy. We know that, right? High angle boundary will have high energy, which has high reactivity. And we have impurities in grand boundaries. There are some impurities like B atoms in A metals. This is called impurity, right? And also the grand boundary engineering. Okay, if you want to have robust material, or you want to have a easy to elongate, to extend it, to make it longer, so you have different way of doing the grand boundary. So that's what we call grand boundary engineering. So this is two-dimensional defects. For the three-dimensional defects, here is the summary. So first one, we have three-dimensional imperfection. We have void, which is pore and cracks, right? And also foreign inclusion means that you have impurities in. This void means it's not impurity, it's vacancy for the one in terms of zero-dimensional defects, right? So foreign inclusions, for the good one, you generate new phase, which is the one you don't like. For the good thing is we call precipitates. Precipitates means that you generate another new phase, but if that phase is useful. For example, we call intermetallic compound, right? Intermetallic compound. We call precipitate hardening. So this kind of small black dots in this alloy is what we call precipitation or precipitates, which is good alloy. Okay. And finally, in the last week, we talked about the chemical origins of the mechanical behavior. So in this region, so there are two types. As we know, for the mechanical properties, we have elastic deformation. We have plastic deformation. Plastic deformation means you change the shapes, or you change the form permanently, right? Okay. And for the elastic deformation, that means that if you change the shape will be returned back to the original shape. In terms of interaction between two atoms, you can regard this region as the elastic deformation region, right? And which is linear, and this linear follow Hooke's law. And when the interaction beyond this region, for example here or here, and this is what we call plastic deformation. And the theory you follow is dislocation or slip, right? Okay, so this is a summary for the three-dimensional defects. And today, we will talk about the section 4.8, atomic vibrations. Atomic vibrations is also a defect, but it's not really what we think is very bad or very good. Why? Because every atom in the solid material is vibrating very rapidly about its latest position within the crystal. That means what? That means atoms will move. This is atom, right? Atom will move. So this is called atomic vibration. Why atom move? And because of temperature, because of energy. You give the energy to this atom, so atom will move. So at any instant of the time, not all atoms frequency, amplitude, nor with the same energy. So this atom move different direction and the different amplitude. Okay, this one might be moved like this one might move like this, and different direction and frequency too. Like this one might move like this very quick, and this one might move slowly. So every atom is individual. You cannot expect everything go to the same direction or same amplitude or same frequency. So this is called atomic vibration. So over time, the vibrational energy of any specific atom will also vary in a random manner. So all the atoms move in a random manner. So that's what we call random walks. So this slide tells us that what's the relationship between the temperature and atomic vibration. Let's start to have the definition of the temperature. What's the definition of the temperature? Temperature of a solid is readily just a measure of an average vibrational activity of atoms and molecules. What does that mean, definition of temperature? That means that if this atom move very fast and the energy is very high, activity, right? Activity is energy. That means the temperature will be high. Okay, so this is actually the definition of the temperature. So at a given temperature, there will exist distribution of energies for a constituent atoms about average energy. So the temperature actually is the average energy of atoms. It's kind of index. Okay, so if the temperature is high, that means the energy will be high in this object or in this metal. Okay, so if the temperature is low, that means the average energy of these atoms will be low. So what happens if energy the temperature go to 0 Kelvin? There's no energy. There's no energy, right? So every atom will be freezed. Atom doesn't move. So there's no atomic vibration. Okay. So the temperature increases, the average energy increases. In other words, average energy decreases, the temperature decreases. Right? So at the room temperature, so let's think of what's about all these factors. At room temperature, a typical vibrational frequency is on the order of of the 10 vibrational per second. That means what? This vibrate about 1 to 13 hertz per. That means 1 to 13 times, very fast. Atomic vibration. The amplitude is a few nanometers, which is 10 to minus 12 meters, which is 0.01 Armstrong. So assume this is 1 Armstrong, right? Think of the diameter of a radius or the diameter of the atom is 1, and this move is about out of 100, and so move raise a little bit like this. Okay, but the frequency is is 10 to 13 hertz. Okay. So what's the atomic vibrations with defects? We also regard this as a defect. This atomic vibration may be thought of as imperfections or defects because it moves. And so you have defects. So many properties and the processes on the solid are manifestation of this vibrational atomic motion. For example, the property of melting of a metal, vibration are vigorous. rupture large numbers of atom bonds. So if you have a high temperature, the temperature reached to the melting point, this atom, the bond will lose. Right? You break the bonds here and atom will be vaporized. Okay? Or this will lose the bond from solid become liquid. Okay? So this is about thermal energy. We'll talk about this in chapter 19. Unfortunately, we don't have next semester to talk. So if you are interested in this topic, please go to chapter 19 in this book. Okay? Right. So this semester, we don't have time to see the video vibration on a molecular cool and trap atom. So let's just like this. Right. So this is the summary of the atomic vibration. Please release by yourself. And then we finish this part in chapter 4. So next part of the chapter is the microscopy examination to see the defects. This section, we want to tell you that what's the tool to see the defects, which is we use is a microscope. So section 4.9 is general. In general, when you see an object or you see a metal, you can see by your eyes, right? But you cannot see you cannot see the details of this metal in the atomic scale or in the microscope scale. So we have macro structure, microstructure. Okay. So here is the important that when you we are engineers, so it's important to show the evidence, the evidence, the things what you have found, and it is important to show him the evidence, which is a picture or image or video, rather than you say 1,000 words, right? So this is important. A picture is worth 1,000 words. So you just show the facts, show the evidence. And today we are going to tell you how to show this picture. Okay, when you see the picture, it worth than the 1,000 words, right? You don't need to write many things. You don't need to tell. So first of all, macro structure. So it is necessary to examine the structural elements and defects, right? Okay, this is a polycrystalline lead ingot. So when you see this, it might be this can see on your unaided eyes. So you can see this by yourself. So when you see this, you might think, wow, the surface is rough because you have many grams, which is very big grams. And between grams, there are some gram boundaries. And on the surface defects, I hope you still remember this. So this is microstructure. You can see the objects with your unaided eyes. And how about microstructure? When you see a brass like this, and it's very shiny, very beautiful. You go to the shop, you want to buy this instrument, and it's very shiny and very beautiful. But when you use microscope to see the details of this brass, you might find, wow, this is not perfect. There are some defects, and which one we call the microstructure. So most materials, the constituent grams are of microscopic dimensions. So microscopic dimension, which is 10 to minus 6 meter, which you cannot see by your eye. So the details of the microstructure must be investigated using some types of microscopes. And so if you use optical microscope and you enlarge this image about 60 times, so you can see the structure something like this. Again, this is the gram. Between grams, you have gram boundaries, right? So this is called brass, right? Brass is the copper and the zinc solid solution. So how about microscopy and microscope? Microscope is a kind of a machine to see the objects. Microscopy is a kind of a study or instruments to investigate of the micro structural features of all the material types. So you can have optical microscopes, you can have electron microscope, you can have scanning probe microscope. So optical microscope means you use light to observe objects. Electron microscope, you use electron beam to observe the objects. How about scanning probe? Scanning probe means you have a small, very tiny tips. You touch the objects and you feel the objects. So when you close your eyes and you use your finger to touch the objects, and you can feel the surface, the roughness of the surface, or also you can feel the shape of the surface. So you can draw the features of the objects by touching. That's what we call scanning probe microscopes. And after you observe, you record it. And this is what we call photo micrographs. So micrographs is a photo micro, okay? Photo micrographs is the graphs on which the image is recorded. So this picture you can show your friends, you can show your supervisor, okay, etc. So microscope examination is an extremely useful tools in the study and the characterization of the materials. Right, so now let's see the technique, the tools we can use to see the microstructure or defects in micro scale. So section 4.10, and the first one, optical microscope. Second one, electrical microscope. The third one is scanning probe microscopy. So this is resolving powers of microscopes. So as you can see with your eye, you can see something which is 1 meter and down to about 100 micrometer. Actually, 100 micrometer is too small. But something like this, you have a very good eyes. You can see the range from 1 meter or larger than 1 meter and about 100 micrometer. So after that, below the 100 micrometer, you cannot see, okay? And you need to get a help from light microscope to see something in detail. So if you want to see a red blood cell, you want to see a biological blood cell, or you want to see bacterial, you cannot use your eye cannot see these kind of objects. But with the help from the light microscope, you can see red blood cell and the bacteria. However, if you want to see a light microscope doesn't help. Okay, and because of the resolution, the power is not that strong. You cannot see more details. In that case, you need electron microscope to see the virus, which is 10 to minus 8 meter, or to see the nanomaterials like DNA molecules. You can see this structure by the electron microscope, or even you can see a single atom or atoms or defects in zero-dimensional defects. So you can use the electron microscope to see the defects. Okay. So first of all, optical microscopy. The microscopy is this microscope tell you that you have object here. I'm sure all of you knows this. This is a reflection light. This is transparent light, transmission light, right? So you have object here. So light goes through the object, and you can see your eyes here. You can see something, and this is a reflection. This is transmission mode. Okay. And I think this is too easy for you. I just don't want to waste your time. So please read this by yourself. So this is called reflecting mode. Reflecting mode. Okay. And normally, this kind of optical microscope, the magnification normally can go up to about 1,000, 1,000. Well, maximum 2,000, but normally 1,000 is the limit. Okay, 2,000, 1,000. Okay, so how are you going to prepare the samples to watch the defects? Okay, you use two ways. The one is called grind or polish. You know, you have an object and you have a sandpaper, right? Sandpaper. So you just do the grind or polish the surface so you can see the surface very well. This is a mechanical method. Okay, and another method is called chemical method. Chemical method is called etching. So you have chemical. You have chemical. You put, and so chemical will polish the surface. So this is called chemical method. So for the etching, this is semiconductor process we call etching, but I don't have much time to tell you this. What I want to tell you is you use chemical agent to remove some of the materials from the surface of your objects. Okay, so you just kind of polish the surface. And especially for the etching, you have certain chemical. The chemical can selectively etch the surface. There are two types. If you have a single crystal specimen, chemical might prefer to go into some certain plans like 100 or 111 or 110. So for the single specimen and also for polycrystallized specimen, etching has a different process. So for the single crystal specimen, the chemical reactivity of the grams of some single phase materials depends on the crystallographic orientation. So if you have different crystallographic orientation, the speed of the etching will be different. However, for a polycrystallized specimen, there's no crystallographic orientation because it's randomly distributed, right? Because on the surface, you have different surface face to the surface, right? So polycrystallized specimen means what? Especially etching characteristics vary from gram to grams. For example, this gram is 1 on surface. This gram has different surface. This gram has different surface, right? So, but however, the weak or which the gram boundary has the highest energy. So for chemical reagent, it's easy to go into the gram boundary first. So the etching rate in the gram boundary will be higher than the etching rate in the surface, in the grams, right? So often along the gram boundaries, regions are more chemically reactive. Okay, so gram boundary will have high chemical active compared to the gram itself, right? So the chemical will go into this gram boundary first. So that's what we call etching. Well, this is just for your information. If you use potassium hydride, we call wet etching. So this is the wafer surface for semiconductor. So this is surface of 100, which is, it looks like this. Okay, when the top view of this surface looks like this, and then 111 it looks like this. 111 looks like this for a silicon wafer, which is single crystal. So when you have a potassium hydride and put on the surface, and which one you think the etching rate will be fast? Which one? 100 or 111? Which one do you think the etching rate will be quicker? Which one? Can you tell me? How are you going to decide the etching rate? Which one will be faster? How are you going to decide this? Anybody want to tell me? There's only one word. If you know, I will be very appreciated. And I will be very happy. I cannot sleep tonight. I give you 1 point in your final exam. I give you 1 point in your final score. Could you tell me what's the factor to decide which one will be faster for the etching rate. Which one? Yes, please. Area. Giri giri. Japanese. Very, very close. But there's one certain word, a term related to the surface. What's that? Thank you. We call planar density, right? If you think of the planar density, if planar density is low, that means what? The etching will be very fast. If the planar density is high, the etching will be slow, right? So if you think of this, if you don't count the planar density, seems this one will be faster than why? Because there are many spaces, right? So the etching, the KOH will go in faster than this one. So the etching rate of the 111 plan or 100 plan will be faster than 111. Depends on you can do the calculation of planar density. Okay. Right. So reflected light, so 0.5 and 1 point. Okay, 0.5. Okay, reflecting light from the 3 etching surface grams is that if you have a surface like this and you use optical microscope, what kind of picture you can get? So if we have a polished and etched surface, you already polish, and the surface looks like this, and this is very smooth. This is a little bit rough. This is the most. This is roughest, most rough, right? Okay, so if you use microscope and the light, this reflecting light, right? Light will go into this and reflect the light looks like this. So what you can get from the top view is you here. Why? Because most of the light return back to this region, and this one will be the darkest because most of the light scattered to another. This region doesn't receive any, doesn't receive many photons. This region is in the middle. So as a result, when you see a picture or a microscope, you can see something like this. So this place is you have very smooth surface, right? Because the light, this has a high density of the photon, and this is the darkest means what? Most of the light scattered. So you have the is rough compared to this one. This one smooth, this one rough, this one between the middle, between this and this, right? Okay. So as you can see, edge surface, this one is bright, looks like this. Okay, ground boundary etching, I just show you this. Please read this by yourself. So when you have ground boundary, that means what? This surface is very beautiful. So you have bright parts, but the dark part looks like a line. Why? Because the light doesn't return back to the place where you receive the image. Okay, so the reason why this place is dark is because light scattered. And as I just told you, the optical microscope has its limit. Why? Because because you can see you can use the microscope, and the resolution can down to about a few micrometers. You cannot go this. You cannot see smaller than this. Why? Because there's a limit to the microscopes. Because it takes a long time to talk about this. It really depends on the diffraction. Okay. And this is about the iris disk. I don't have time to talk, but what I want to tell you is that when you have light scattering and distribution, so light intensity distribution will look like this. So this is called iris disk pattern. You have spotlight like this. Okay, so you have a light distribution, intensity distribution. However, if you have two spots very, very close, and the iris disk will be overlapped. So once these two spots very, very close, it looks like one. Use optical microscope because of scattering reason. Okay, so that's why you have limit for the optical microscope. So please read this by yourself. I just try to finish this chapter today. So it's something to do with what we call numerical aperture. This is very important in the semiconductor industry. It's related to the, when you say about semiconductor industry, when you say about the devices go to the 5 nanometer, 3 nanometer, and 1 nanometer, is really depends on numerical aperture of your EUV machine. But anyway, if you are interested on this topic, this when you have when you go to the graduate school, right? So, because the limit of the optical microscope, you want to have a better resolution. You want to see some more details in nanoscale. So you need the help from electron microscope. There are two types. The first type is called scanning electron microscope, which is refraction mode. You can regard this as kind of refraction mode in optical microscope. And another one is called transmission electron microscope, which you can regard the light transmit to the objects. And now is the electron beam transmit to the objects. So we call TEM. One is called TEM, one is called SEM, or you can call it SEM or TEM. Okay. So electron microscope, the one is that the image of the structure is formed using a beam of the electrons instead of the light radiation. So you use light, right? Light, it can be blue light, the white. But for electron, this use electron beam instead of the light radiation. And what's good about electron? Electron is, the speed is fast. Is fast, same as the light, right? Okay, but the wavelength is much, much smaller than visible light. The wavelength of the high velocity 0.003 nanometer. And if you know, when you use the light or the photon, the wavelength is about 400 to 700 nanometer, which is much, much larger than the 0.003 nanometer. So when you think of the X-ray, the wavelength of an X-ray is about 4 angstrom. And this is the X-ray, the wavelength of X-rays is larger than the electron, the wavelength of electron. So as a result, electron will have a better resolution. Okay, so you want to use the electron microscope. And also you can tune the speed of the electron. You cannot tune the speed, you cannot change the speed of the light, but you can change the speed of the electron. By what? By applying the voltage potential, right? Okay, so you can accelerate it or decelerate it across the voltage. Okay, and at that time, because the wavelength is very, very small, so the wave-like behavior will much, much greater than the particle-like behavior. So microscope, because of the short wavelength of the electron beam, you have high magnification, which is we call numerical aperture, something like this. Okay, so electron beam is focused and the image formed with the magnetic lenses. So, when you want to change the direction of the light, you use mirror or use a piece of glass, right? And you change the direction of the light. But how are you going to change the direction of electron? By magnetic lenses. So geometry of the microscope components essentially the same as the optical system. For the electron microscope, the first one is called reflection beam mode, which we call TEM. The second one is transmission mode. We call it, we call it TEM. This second one we call it TEM, transmission electron microscope. Reflection beam mode we call TEM, scanning electron microscope. Right. So let's go to the first topic, scanning electron microscope. So this is a schematic of SEM. The SEM looks like this, and you have a monitor here, so you know the size of this machine, right? So you have a beam generation, you have the electron beam generator, so electron emitters. So you shoot the electron beam from here, and you go to the condenser lens, goes to scanning mechanism, and change the direction. You increase the speed or decrease the speed from here, and eventually the electron beam hit the specimen. And you have a detector to collect the electrons. So depends on the intensity of electron, you can generate what? You can generate image, which is the same concept as the light, right? Microscope, optical microscope. I'm trying to tell you all the details. So what I want to tell you is, if you want to change the direction of the, direction of the electron beam, you use what? Magnet. If you want to change the speed of the electron beam, you use what? You use voltage. Increase voltage or decrease the voltage. So you increase the speed, decrease the speed, and change the direction. So you can use this beam to do the scanning on this, because electron beam, the spot of the electron beam is very small. So you cannot observe a big object. So if you want to observe a big object, scanning, right? The electron beam will scan on the surface, and you can collect this information from the detector. So this is what we call scanning electron microscope. So the image formation by SEM is that here, and then electron generated by this, and the focus and decelerated and impact on. Okay, so you got the figures, and you do the scanning. You know, electron beam is so small, so in order to observe the scanning on the surface. Right. So I'm sorry, I need to skip this. How about the preparation of specimen? This is the way to prepare the specimen. And then again, you need to polish the surface, the defects, or you need to do the etching in order to see the specimen. Okay, so the magnification of SEM is from the range from 10 to about 800,000 times. So what's the idea of 800,000 times? Which is about a nanometer scale, 1 nanometer. You can see something which is about 1 nanometer. So information provided is what? The surface. So you can see the differences between 1 nanometer area. And also, not only this, you can qualitative and semi-qualitative analysis of the elements composition of the very local surface area. So you can see this is copper and this is gold by X-ray, by the emitted X-ray. So this is how it looks like. You have monitor here. You personally see here. You load this place to this place, and you let gun here and generate electron gun, and the electron beam will shoot from the top to here. Detector and detect the information back to the computer. Show you the image here. So let's take a look how it looks like. This is the head of a human being, right? Obviously, this is, this has a gold hair. So if you take a look like this, you can see by your unaided eye. However, if you want to see a single, and you want to see the quality of her or his hair, you can pull out one and put it into the microscope. And microscopy tell you that the information is quality of this hair. So as you can see, I don't know this quality of the hair is good or not. Okay, but there's some information I want you to know, and this might be, or I mean 50-50. This I will show you an image, SEM image. I want you to tell me the information you can get from this image. Okay, so what I want to tell you is scale bar. This is called scale bar. Scale bar, and here is 10 micrometer. 10 micrometer tell you that from here to here is 10 micrometer. Okay, what I want to ask you is, please tell me the diameter of this hair. Anybody can tell me the diameter of this hair? What's the diameter of this hair? Can you tell me? Of course you can, right? Because from here to here is 10. So 10, 20, 30, 40, 50, 60, probably 70. Okay? About 70 micrometer, right? But if you write 50 micrometer, you got a point, no problem. But if you write 10 micrometer, I'm sorry, I cannot give you, this is not a correct answer. So roughly from, well, I would say roughly from 70 to 80 or from 60 to 90, that would be correct answer. It doesn't need to be exact unless you have a ruler to measure the radius, the real size, right? And this information tell you the energy, the voltage of the electron beam, which is 10K volt. 10K volt. Okay. So this is the energy, and well, this is sequence. Next picture will be 0.0412. Don't worry about this. Is the voltage of the electron beam, and also the scale bar. And this is called W distance, working distance, about 15. You don't need to worry about this. Right, so there's some information you need to know is, materials looks like this. For example, which is made of ceramic. If you use microscope to see this, you will feel ceramic. Many small particles get together, stick together, and make it become like this. That's why when you pour the water in, the water, and it looks like so you understand the water go into this and absorb this container. So this zeolite is one type of material, okay? And this is a solar piece or the solar panel. Not only you can see ceramic, inorganic material, but also you can see organic material. Like this is polymer fibers. Your fibers, the clothes you can see, and this is standing wave. Don't worry about this. This is also semiconductor material, photoresist pattern. And you can see something spherical. So can you tell me what's the size of this sphere? Can you tell me what's the size of this sphere? First of all, take a look of the scale bar. Where is the scale bar? From here to here is 10 micrometer. So the size of this copper is what? Copper sphere is about 10 micrometer in diameter. Right? Okay? And what's the magnification? Magnification here is X 2000. This is magnification in large. Okay? Let me show you here. This is scale bar. From here to here is about 2.99 micrometer. And magnification is about 10K. 10K. 10K is what? K is 1,000, right? So it's 10,000. Okay, 10,000. times larger. Okay, and this is 5 kV is what? 5,000 volt. That's the voltage. Okay, let me show you. Okay, and this is semiconductor. You can see the semiconductor. The cross section of the semiconductor here, and this is the top view of the semiconductor chip. Okay, but biologic materials, the wing of the butterfly or the pollen, okay, and the leaves of a plant. So you can see this, and virus here. I don't have time to tell you details, but equip some tools, more information from SEM. So you can extract from the SEM. You scatter the electrons from SEM. So you get the information of this and read this information, and you can explain this information. Okay, so these are the information you can get from SEM. You got the morphology. From the backscatter electron, you got the elements you observe. Okay, from EDS is the X-ray information. You got, again, you got elements. WDS is also, okay. Electron backscatter diffraction patterns, you can see the grain orientation. And this is called chesoluminescence. You can get some kind of impurity or some kind of defects information. Okay. So next topic is transmission electron microscope. But before we go to this topic, let's take a look. So let's talk about transmission electron microscopy. So this is the schematic of the TEM. Actually, a TEM impulse in the middle of the electron beam. So the electron beam will penetrate or shoot through this sample or specimen and then reach the detector. And you collect the information from the detector by CCD or by whatever, and you get the information. So you see the surface, you see the image. Okay, this is how it looks. And the formation process of the TEM image is that, again, you generate electron beam, and then electron beam will focus and accelerate or decelerate with the magnetic lenses, and the beam passes through the specimen, and the transmission beam is projected onto a fluorescent screens or a photographic films and form an image. Okay, so the specimen, again, you need to polish. You need to do some treatment. Okay, so the magnification of TEM will be higher than the SEM. So this is very good machine. You can see in atomic scale. You know, SEM can only see the scale in nanometer, but TEM can see the scale in atomic scale, in Armstrong scale. Okay, so this is the configuration, and this is how it looks. TEM machine looks like. You know, as you can see, the gun is bigger than the gun is bigger in TEM machine compared to the gun in TEM machine. Of course, because electron beam need to transmit to the through this object, so electron beam require high energy. So these are some images to show you the TEM image. As you can see, this is a magnesium oxide crystal. It looks like a cube, but as you can see something barely inside. So if this is electron beam is very strong and transmits through this crystal, so you can see in this crystal or not. Okay, and this is called MCM41. This kind of porous materials. As you can see, you have some channels in this material. Okay, so if you use SEM, you see nothing. You can see a black only. But if with TEM instead of SEM, you can see through this something inside. So again, you can see some bacterial you can see some biomaterials. And also, even more, you can see a crystal structure. This is a silicon nitride. You can see this, all the black dots represent a single atom. And you can also see the this or lattice interplanar spacing. And you can measure the distance between interplanar spacing. Here is about 3.14 angstrom. So according to interplanar spacing, you will be able to know the age. You will be able to know what's the plant you are watching. So compared to this is germanium silicon. So TEM is a very powerful machine, but very expensive. So compared to the SEM and TEM, as you can see, you put the objects sample in the end of the beam, but if you for a transmission electron microscope, you put a sample between in the middle. So these are two different microscopes. You see that the differences. So here I just want to show you an example using a carbon nanotube as a material. This is the SEM image. Could you please? It looks like a tube, right? Or a rod. Rod is solid inside. Tube means is hollow inside, right? Okay, but when you see SEM image, you don't know it's empty inside. Is hollow tube is a kind of tube or is a rod? You don't know because you don't know what's going on inside this material. But here I can tell you is that, could you please tell me the size of this, the diameter of this rod or this tube? Can you tell me this? From here to here is about 100 nanometer. So the diameter of this tube is about what? It's about 20, right? 20 nanometer. Okay, see this one from here to here is about 10 nanometer. Is 10 nanometer. 10, 10, 10, 10, 10, 10. So you have 100 nanometer from here to here. So this diameter is about 20 nanometer. Okay, and X 500,000. This is the magnification, which enlarge 500,000 times larger. Okay, and this is 30,000 is 30,000 kV is 30,000 V is the voltage of the electron beam. Okay, so this information, please remember this information. So when you, this is SEM mode. When you use the TEM, you will see something like this. And you get more information from TEM. Why? Because you can see inside the tube. And actually, this is a tube. This is not a rod. This is not a solid rod. This is a hollow tube. So you see something inside. So if I want to ask you, what's the inner diameter of this tube? Can you tell me this? The inner diameter tube is about what? It is about 5 nanometer. Why? Because from here to here is about 10 nanometer. So the size of this hollow tube is about what? It's about 5. Right? Okay, so you can get more information, and you can tell me. Then you got points in your final score, in your final exam. Okay, so if you enlarge 500,000 to 800,000, you can get more details. Actually, this one is it's not a particle, it's a hollow ball, right? It looks like a hollow. It's a kind of, we call a carbonyl capsule. Carbonyl capsule. Okay, so these are the information I want you to tell me in your final exam. So you can get, if you tell me more, you get more points in your final exam. Okay, of course that TEM got Nobel Prize, and again, a few years ago, we have a kind of cryon. Cryon means that temperature go to 77 Kelvin. You can see more details because you reduce the atomic vibration between atoms. So you see more details in terms of atomic point of view. So they got Nobel Prize because they use this very good technique to observe many things. Right, so this is summary of the SEM and TEM. There's another one important topic, which is scanning probe microscope. But because I don't have time to talk about this, I'm thinking to skip this topic. And actually, this is important. This is a very interesting topic because instead of using electron beam or photon beams to observe objects, it looks like you close your eyes, you see nothing, but you can feel something. You use your finger to feel something, and this finger is very small, which is the tips of the finger is very small, down to a few nanometer. Okay, so this is the probe here is very small, so you can feel something. So when you feel something, what does that mean? When you feel something, that means this is the interaction between two atoms, right? So if your probe go to the object and you have interaction between the tips of the probe and also the surface of the probe, surface. So you have many interactions. The first important interaction is the force, right? So that's why we call atomic force microscope. And tips is very small. This is very small, right? You have tweezer. And tweezer is the end of tweezer is very small. This is already very small, and you have something come out from here, and then it's already small, and then even smaller. The tip is even smaller. Okay. So this is the members of SPM. You can have using different sensors like scanning tunneling force. This is quantum mechanics phenomenon. Scanning tunneling. Okay, this is Coulombic. This is van der Waals force. This is lateral force. This is magnetic. This thermal interaction between two ends. This end and this end. And this is electrical force microscope. And you can also have a near field microscope. We call ENSOM. Okay, so this all together is called scanning probe microscope. Probe using different forces, tunneling forces, atomic force, van der Waals forces, lateral forces, magnetic forces. Okay, so you can have many type of microscope. Right. So so this is the machine, very small, not that easy compared to TEM or SEM. So they get Nobel Prize very soon. They invent this within 5 years. They got Nobel Prize, which is within 5 years you got Nobel Prize, which means what? All the scientists recognize this work, and they want to give award to this gentleman for this. So this is the image of AFM. You can see carbonyl tube between. This is the germanium silicon, which is the phase, very small. You can even see the atomic one by one. This one is one atomic. This is electron C. So not only this, you can manipulate the atoms. You can put atoms together by interaction chips and one single atom. So you put atoms together, you can make a circle, even make a Chinese character. This represents atom, right? 原子. You put the iron atoms on the spur. Okay? So you can make a figure of Taiwan if you want to. So not only you can put this together, but you can also, because if you make a picture, if you have 30 pictures or 100 pictures, you can make a what? You can make a movie, right? I'm sorry, I don't have time to show you this, but if you go to YouTube, you can see the world's smallest movie. Okay, they put atoms together, then put 100 pictures together and make it become a movie. They call it world's smallest movie. The temperature down to 5 Kelvin, because you don't want to add this, right? So the temperature need to go down to very, very low. And in this case, it's about 5 Kelvin. Okay, magnification is about 100 million. Okay, very, very small. And you have 240 frames. And this movie is about 90 seconds. Okay, and the reason this is called, this is oxygen. This is this surface is copper. Okay, so this is summary. Okay, this is my university. The university I stay is the town, or we call Putney Bridge. Very beautiful. Please take a look if you have time in the future. If you go to United Kingdom.